Okay, so our first homework is going to be out either tonight or tomorrow morning, and it's going to be due like a week from now. And yeah, so that's the first homework. And this Friday afternoon, we are going to teach you a software called AVL that essentially does what we are going to be covering today. That's basically, well, it does a lot more than what we are covering today, but like it'll do, part of its job is to do what we are covering today, which is computing how much lift and the induced drag and also aerodynamic moments an airplane has, right? Given its the distribution of things like twist, span, and chord length, etc. On the airplane. All right, so let's get started. So just a reminder of how we finished in the last lecture, right? So we asked you to compute the velocity field, actually velocity at 5 points, and on the wake of an airplane, assuming that the wake of the airplane is dominated, is actually composed of the free stream plus the induced flow from these two vortices, right? Both has a strength, which means a circulation of gamma. Do you still remember what a circulation of a vortex is? A circulation of a vortex is if you integrate the velocity over a circle around the vortex, right? That's the integrated velocity. And by the way, integrating a velocity along a curve of length 2 pi r, so if you are integrating along the length 2 pi r, basically has a unit of velocity times length, right? Okay, and because the velocity decays inversely proportional to the radius around the vortex, so it doesn't matter, and the length of the integral is 2 pi times radius, right? So it doesn't matter what radius you are integrating. If you integrate over a bigger radius, the velocity is smaller, but the length of the integration is proportionally larger. So no matter where you integrate, you get the same circulation. Okay, so we have two circulations, two vortices, both of the same circulation, and I ask you to compute the velocity at the 5 points. So you went through all the algebra to compute it, right? But today I'm going to redo this calculation for you, but using a different method, a more geometric method of doing the calculation. So hopefully both ways you're going to gain a little bit more intuition on what the flow around the vortices are. Okay, so here, this is the formula for the velocity field around a single vortex, right? But as we also discussed back on Monday, you can think about this velocity field as a vector that's perpendicular to the radial direction and has a magnitude. That's what? So what is the magnitude of this velocity field? Yes, the magnitude is gamma divided by 2 pi, and how does it depend on the spatial location? Yes, it's 1 over the distance, actually, right? The distance of that spatial location to the vortex. All right. Okay, so that's nice, because then we can actually use a geometric way to figure out, for example, the velocity at the first location is basically the summation of two identical velocities, each one coming from one of these vortices, right? Okay, now we know it's exactly downwards because the downward velocity is perpendicular both to this radius and to this radius. All right, and what's the magnitude? The magnitude from each one is 1 over the distance, which is half v, right? So the velocity field is 1 over b over 2 plus 1 over b over 2 and is pointing downwards. So that's the velocity at the center location. All right, questions? How about point number 2? Okay, point number 2 has two induced velocities again summed together. So one velocity is pointing here, which is perpendicular to this radius, right? And it is going to have a magnitude exactly 1 over b over 2, because we are saying, okay, these are forming, all of these points form equilateral triangles. So the distance from point 2 to the center of this vertex is actually b over 2. That's why this. Oh, I'm sorry. I didn't multiply by this gamma over 2 pi, right? Okay. So this is yeah. I need to. Yeah. I forgot about this. So the velocity induced by the left vertex is 1 over b over 2 times gamma over 2 pi. How about the velocity induced by the right vertex? It is pointing towards this direction, right? And it has a lower velocity. It has a lower speed because this point is further away from the right vertex compared to from the left vertex. So how much more further away? Well, if you do a little bit trigonometry, right? Anybody can do trigonometry from your mind and tell me how much further away? Square root of 3, exactly, because like we actually have a have a normal triangle here, and a triangle of 60, 30, and 90 degrees over here. So we actually have a square root of 3 over 2b, right? A distance. So as a result of this, the velocity going going downwards slightly to the left is actually 1 over square root of 3b over 2 times the same gamma over 2 pi. Okay? All right. And you can see that again, if you compute the compound velocity, right? Again, this is going to be a 90, 30, 60 degree triangle. Okay, and as a result of this, the total green velocity is actually twice the amount of the orange velocity. So the total velocity is going to be, well, gamma over 2 pi times twice of that, which is going to be 4 over square root of 3b. All right. Okay, so maybe like if you can't catch the trigonometry, I recommend you just do it again after class. Okay, and so if you are familiar with, if you are kind of a geometric thinker, okay, this is actually easier than the algebraic way. If you think more algebraically, then the way we did back in class on Monday is going to be easier. So both ways are going to produce exactly the identical results. Okay? All right. Oh, so sorry, and also the direction of this is actually pointing exactly towards the center. All right. Yeah, this is there is a lot of geometry and trigonometry involved, and then the velocity field from here is going to be exactly symmetric, and from here and here is also going to be symmetric. So basically, end up with a flow field where you have two velocity points towards the center. The center points down, and the velocity here points exactly away from the center. All right, got it? Okay, so this is basically what we did in last class, and one of the questions is, how about the velocity everywhere? This is just the velocity on 5 points, right? Okay, for velocity everywhere, well, one thing we can do is to use computers. So how many of you use decimals? Everybody, okay, great. So for example, here we can just code it up, right? We can just write the formula over here. So for example, let's actually focus on the y velocity. Okay, focus on y velocity. We are going to have gamma, well, let me just say g over 2 pi, okay? And we are going to add this gamma as a variable, and the y velocity is x minus x naught. So x minus, so x naught for the, let's do the right vertex first. For the right vertex is b over 2, right? And we're going to add b, and it's, let's make it positive, okay? All right, and then it's going to be divided by, well, x minus b over 2 square plus, let me actually take the vertical coordinate. Let's denote it as z, because usually for airplanes, z means the vertical direction, right? And let's see. Okay, so it's actually z minus z naught squared, and z naught is 0. Okay, so plus z squared. And instead of adding something, let me just call this a function. So velocity x and z, I'm going to define it as this, and I'm going to say velocity of x and z observation, and I'm going to add this, right? So essentially, if my observation point is 1, let me actually make a big gamma. If my observation point is 0, right, I'm going to have when observation is close to 0, I'm going to have a very large velocity right outside of the vortex, right towards the right of the vortex, that's going up. Right inside the vortex is going down. So let me actually make my z to be minus 1 and 1 with a small step size. All right. Okay, so this is the velocity induced by the single vortex sitting on the right, near the plane of the vortex. Okay, let me then add the other vortex. So minus, because my g is negative, and instead of minus a, so instead of minus a b over 2, I'm going to minus b over 2, which is plus b over 2, right? And here I get plus b over 2. All right. So here, what we are seeing is the velocity field. Let's zoom in a little bit. So this is the velocity field, downward velocity field, between these two wingtips. And of course, the further away I go on up and down, the less influence the vortices have. The closer to the plane, I have more speed both downward in between the vortices and upward just outside of the vortex, right? So just to get you a sense of how dramatic this downward velocity and the upward velocity outside of the vortices are, let's actually take a look. What actually happens if you actually fly something near these vortices? So here we first are going to see a helicopter flying by, and the vertical flow is actually not just for airplanes. Any lifting body, right, through conservation of momentum, is going to induce a vertical flow in its wake. So the helicopter is already here, and here comes the small airplane. So as you can see, the helicopter actually flies on the right, towards the right, like offset to the right side of the runway, right? So its left wingtip vortex over here is actually going to be closer to the runway. And there might be a little bit wind that kind of shifts these vortices towards the runway. So the airplane flying behind it is actually got hit on the left side of this vortex. So its right wing is going to be in a very strong downwash. Its left wing is going to be in the upwash. That's what's causing this crash. Now we're going to look a little bit into how strong these vortices are. Okay, and to understand how strong these vortices are, we actually need to link the strength of the vortex to how much lift the airplane is getting. Okay, and this analysis is actually going to be very similar to the model we looked at last week. That is kind of assuming there is a cylinder of downward flow, and you can see that when you are explaining, when you're modeling the wake of the vortex, wake of the airplane, not as a cylinder but as dominated by vortices, the way you analyze it is very similar, except you have to use some calculus. Okay, instead of just multiplying the mass with a fixed velocity to calculate momentum in the downward moving cylinder, now we actually have to perform integration on the non-uniform moving flow. Okay, and this is another motivation to use the algebraic way of expressing velocity instead of the geometric way, because for an algebraic way it's actually a lot easier to do calculus with. Okay, so let me first answer this question. For this flow field, what is the total amount of vertical momentum in a thin vertical column of air extending far up and down in the wake of the aircraft? So this is saying, if you look back onto decimals, I'm looking at one single column that sits, for example, over here. Let's, for example, sits right in the middle, extending all the way up and all the way down. So if you change the z observation, right, the velocity is going to change as a function of z. So I have to integrate all the velocity, all the momentum that differs as a function of z to get how much total momentum I have. All right. So is it clear what we need to do here? We're looking at a vertical column, and the velocity here might be smaller. So we are only looking at the y velocity, right? So if we only look at y velocity, the velocity is smaller, bigger, 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 and smaller again. So we have to sum up all the vertical momentum in this column. Okay, so what is the formula? The formula is we are looking at, well, we already have a formula, right? The downwash W as a function of x and z, right? We need to integrate over z. dz goes from minus infinity to infinity, okay, times a small delta x, a small delta y. So in this x direction and y direction. So this is the dz times delta y delta x is the volume, right? And this is the velocity. So if I multiply by rho, that is how much momentum do I get in a small vertical column of area delta x times delta y. So let's first maybe do it in decimals, right? And of course we will leave the rho delta x delta y away and see if we can just compute this in decimals. We are going to integrate minus infinity to infinity and wxz dz. Decimals takes a while, but it ends up getting me this red curve. What does it mean? So the red curve basically is 0 outside of the half span, right? It goes all the way to minus half b, and suddenly becomes, what is the value? It suddenly becomes about minus 1.2, right? Just the value of the circulation between the left wingtip and the right wingtip. It goes back to 0. outside of the two wingtips. Okay, just looking at the graph, can you think about how much total momentum do I get in the entire wake? And how does the total momentum, what does the total momentum depend on? So if I make B to be larger, it takes a while for this to update. So the width of this downward air, right? I should say the width over which the total momentum in the vertical column is downward has a span exactly equal to the span of the airplane. Okay, and the amount of total momentum per unit area, right, is equal to rho times the circulation of the vortices. Let me just write it down. This is equal to rho times delta x times delta z, delta y times either minus gamma or 0 if x is in between. Why do I get this? In between the wingtips, or if x has an absolute value that's greater than the wingtips. Does this make sense? At least that's what we saw from Desmos, right? And of course, we can prove it mathematically once we know what we expect. Right? Let's just go back to Desmos. We are basically integrating this exactly, right? And what we saw is a function that is piecewise constant. Outside of the wingtips, it's 0. It's flat at 0. Inside of the wingtips, it's minus gamma. If you change gamma a little bit, make it 1.3, and this is minus 1.3. Make gamma smaller, 0.7. This is going to go up to here, 0.7, right? And the B basically controls, well, if B is equal to 1, well, B cannot be minus for sure. If B is 1, then this is exactly, has a span of 1. Okay, so now, if this formula is true, we are going to work out what is the total amount of momentum. But like before that, maybe I will spend a little bit of time showing why this formula is true. Okay, and this is kind of I'm doing this for you because it's the first time we use calculus, and in the future, like you may be asked to do calculus on the whiteboard. All right. Okay. So first of all, this downwash is a combination, is a contribution from two vortices, right? And we know the integral of the sum of two functions is the sum of the integrals, right? So let's just do this integral for one of these vortices and figure out what is this integration from minus infinity to infinity, and one of the vortices is gamma over 2 pi. I don't know why it is doing this for me. Gamma over 2 pi x minus half b over x minus half b squared plus z squared, and I'm integrating over dz, right? Okay, so whenever you see a complicated integral, the first instinct should be somehow change the variables to make the integration simpler. Okay, and here what makes the most sense, if you have done such integrals before, what change of variable would you like to actually make to make the integration easier to deal with? Sine and cosine, that's actually very good intuition. But like before that, there is something you can do to actually, I mean, you can directly do sines and cosines, but the sines is cosines of what, right?
Write x minus b over 2 equals to sine no.
Something like that, right? Something between z and x minus b over 2. So the first thing I would do is actually express, instead of instead of dz, I'm going to express it as dz over x minus b over 2. All right, that makes the variable I'm integrating dimensionless, right? It's a z over another spatial coordinate. So if well, the bound of the integral is still going to be minus infinity to infinity because scaling z by something doesn't matter, right? But now, if I divide the dz by this variable, I need to multiply the same thing somewhere else, right, to make it equal. And the place I'm going to be multiply is, of course, I'm going to square the numerator. Okay, and the denominator is still the same, x minus half. Oh no, the pen is doing something weird for me. Let me just see if I do this and this, if this goes away. No, it doesn't go away. Okay, square plus z squared. Okay, now a further simplification is that if we divide both the denominator and the numerator by square of x minus b squared, right? And at the same time, I'm going to move the gamma over 2 pi out of this integral. What I get is 1 over 1 plus z over x minus b over 2 squared, and dz over x minus b over 2. Do you agree? Here we can already see that this whole thing actually so one thing here, I think I missed the one thing, that is when I scale the variable by something, right, it also matters whether this variable is positive or negative. So if I'm dividing dz by something, the bounds of the integral might switch from minus infinity to infinity backwards if I'm dividing by a negative number. So there is actually a sign of x minus b over 2 in front of this, and this is also in front of this. But other than this sign, we can already see that this thing doesn't depend on x, right? If I do a change of variable, say this is my z prime, this is dz prime, so it doesn't depend on x at all. The only thing that depends on x is the sign. Okay, and to perform this integral, you are right. The best thing to do is to do another change of variable. Think about z over x minus half of b as tangent of theta. This is because if this is tangent of theta, I get 1 plus tangent theta squared, which is what? Well, 1 plus tangent squared is like the square of the hypotenuse, right? Okay, assuming that the one side is 1. So this thing is actually 1 over cosine squared. And you have 1 over, so this whole thing is cosine squared. Okay, and anybody remember what is the derivative of tangent? 1 over cosine squared. It exactly cancels with the cosine squared over here. So you get d theta over here, right? Okay, okay. And how does theta vary if tangent of theta goes from minus infinity to infinity? for what angle is tangent theta minus infinity? Yeah, minus 90 degrees minus pi over 2. And for what angle is it positive infinity? Positive pi over 2, right? So this integral turns out to be just equal to pi over 2 minus pi over 2 is equal to pi. All right. Okay, got it? Okay, so this whole thing is equal to just gamma over 2, because the pi cancels, times the sine of x minus half b. So this is from half of the vortex on the right hand side, right? So essentially, if you think about the total function, I get half of gamma over 2 here, I get minus half gamma over 2 here. Now for the left vortex, it's exactly the same but opposite. I get half of pi over 2 here and plus pi over 2 here. So essentially, outside of the two vortices, the induced flow has a total momentum that cancels with each other exactly. And inside of these two vortices, they supplement each other perfectly, each with half the strength of the vortex. So if you add it up, it's going to be exactly the green function over here. Okay? So that's kind of the calculus we need to do to arrive at this conclusion that can be already seen in decimals. Okay? So I'm going to save it and just copy a link and post it on here, so that for future reference. I don't need this. Okay. Now it's a question for you. Okay, you come up and use this conclusion, use the green conclusion to figure out, now what is the total amount of momentum in the entire wake per unit length in the direction of flight? Right? This green conclusion is only on a small vertical column, right? Now I want to integrate again in the other two directions. So what is the total momentum? And then derive from there what is the lift on the airplane. And then how does the circulation depends on the lift span and the flight speed. Okay, come up, form teams of two, and today I have colorful chalks for you. So now it's easier to distinguish your writing from your neighboring team's writing. And if you want white, there are still white over here. White chalks is here, colorful chalks here. Yeah, go ahead. So teams of 2 or 3 people, preferably 2 people, but if we have odd number of students, 3 is fine. Yeah, can you leave some space for another team?
Thanks, guys.
Yeah.
Oh, wait.
Are we doing this with thinking about the helicopter and like the vortex that creates and that's effect on the airplane?
Yes, it's basically we're looking at no matter we have helicopter or airplane, right? The wake is described by these two vortices. That's our model right now.
And like in this, would the airplane be flying?
Yeah, fly in this direction, exactly. Yes.
So are we to basically take like the column and it's just traveling like into the plane?
Yes. Yes. Yeah, by the way, the airplane is flying right into this screen, right? We're looking at the wake from behind.
Can we find the momentum? Like the momentum is like negative.
Yes. Yeah.
Why are we doing? Are we saying this is Z and this is X, and Y is into
Yes.
the?
Yes. Why the airplane is flying right into this?
Okay. So it's per unit length, right? We're supposed to find momentum per unit length.
Yeah, per unit length in that question means per unit length in the flight direction, right?
So it would be like all this. Negative or positive? Over D. Because that's a per unit length.
Are we closer or are we far?
The unit is a little bit so okay. So yeah, you should be integrating. This is right, but like you have two integrals, there should be two d's, right? There should be a dy, right? And then you're dividing by dy, which means this goes away. So this is actually the answer.
Oh. Okay. Okay.
Right.
No, I don't think so.
That was the like magnitude. Right.
Yeah, this is right. This is right.
Oh, okay.
Rho B.
I feel like I understood everything when he was saying it, and not to regurgitate it.
Yeah. Yeah. So this is gamma, right? This is gamma.
The whole integral?
The integral on this side, right, is either gamma or zero, depending on.
Right.
Yeah, outside of this is zero. So
But it's
yeah,
inside. So it's
inside is
gamma.
just the gamma, just the minus gamma. Yeah, minus gamma. Yeah,
Okay,
and then you still have dy, right? So yeah,
so
delta y. Yeah. And y is the direction of the flight. So you are looking at how much momentum you have per unit y direction. And here you are looking at over a y direction of delta y. So if you divide it by delta y, that's the answer.
Over 1 unit.
Oh,
Yeah.
I got you. Okay.
Yeah.
Thank you.
Yeah. Good.
Wait, guys.
So now we just
Oh, wait. I think you have it down there. It's Y, so X.
Oh, I think it's
Yeah, it's 0 everywhere.
Nice. What have you worked out so far?
Not really.
Oh, nice.
No.
Is this something you derived or just recalled from memory?
Neither. We kind of reasoned through it.
Okay, this is
Because
good.
it's just we have the dx here that we're also integrating over it. So
Yeah.
BV.
Yeah.
We're just discussing the units because the units are okay. It'd be kilogram meters per second squared.
So what is the unit of gamma?
Meters squared per second. Yeah. You're integrating velocity over distance.
Yes.
Okay. So meters squared per second.
Yes.
Okay. Okay.
So gamma is velocity times length, right? So now you have velocity squared over here. Rho v squared is pressure, right? and you have B and another length.
Yeah. Okay.
So it's pressure times area.
okay. Gotcha.
Right.
Like the y distance.
Yeah. Oh, sorry for that. So we already worked out the integral, right? So this with only dz is actually equal to either minus gamma or 0. So this function is already derived in the whiteboard.
I did.
You can even just change the bounds if you want for the dx.
Yeah, that's right. You can change the bounds because outside of this minus b and minus half b and half b, this integral is 0, right? So there is no contribution. Yeah, that's right.
So it's just minus b.
Yeah, this is good. This is very good. So are you at the second question now?
We have type change.
Yeah, the first question, I think you have the right answer. You have any questions on this? No? Okay. Not the first one. Okay.
And this is.
Oh, so
We're very confused.
right. So basically, to answer the first question, right, you are integrating the momentum, which is rho times w times dx dy dz, right?
Yeah.
Okay, and you need to integrate in all three directions. But now, one of the directions is already integrated for you, right?
Yeah, and that's what
It's
we
already
got at
done.
the end, right? Yeah.
That's
so
why
is that
you.
what this is?
Like if you're just generally.
Why is there a sign? Oh, it's actually the sign, the sign either plus 1 or minus 1. It's not sin.
Oh, that actually makes sense.
Yeah.
Okay.
Yeah. So remember, like when we see this sudden change, right?
Yeah. Okay.
And by the way, the sign actually doesn't appear over here. The sign actually gets cancelled. I mean, this is only one of the vortices.
Yeah. Okay.
And when you add up two vortices, you get this or this, right? So outside of these two vortices, the signs either plus 1 or minus 1 from the two vortices cancel with each other.
Okay.
So they become 0. And inside of these two vortices, the two signs are the same, right? They are both minus 1, and the magnitude is also the same. So if you add them up, it's just a minus gamma. So this is the result. Don't use this. This is like an intermediate result for us to prove this.
Oh.
Yeah. Oh, okay. So here, v dt dy. This is there is a problem in this. The unit is actually not correct. Yeah. So the lift is how much. The force is momentum per watt. Unit time. So here so this is the amount of momentum the airplane leave in the wake over this much time.
Okay, so we just shouldn't have this.
Yes, you shouldn't have this. Just to divide it by. Yeah. Okay, very good, very good. So this actually tells you why the helicopter is so much more scary than a fast airplane, right? You have fair amount of lift, you have slow speed, and you have a small span. All right, you are good. Yeah. So and the integral should be. Remember, the integral, you are integrating dx and yeah, exactly. X only has non-zero contribution from that's right. So instead of x, you have okay.
Then we should have
Gamma times So this is you're integrating a constant over what distance? Distance of b, right?
Yeah.
So it's the constant times b, right?
Oh, fine. Okay.
The first question is the business velocity of
And don't forget the rho.
along here, and so
And you're integrating x, you still have dy, right?
momentum is k and mass times velocity.
But like we are looking at a unit length in the yes, multiplied by like a unit length in y. So just the
multiplied by the span.
so just the one, right? Yeah.
Oh, just one?
Yeah. Because you are integrating this, which doesn't depend on y, right? Over a unit length of one.
Oh,
A unit length means a length of one.
okay.
So you don't need the integral anymore. So that's the answer for the first question. Just the minus gamma b times rho. Okay.
That,
Yeah.
that basically is kind of like what creating this, because like equal and opposite reaction, you have one. So
Yeah.
changing momentum over to
Yeah. And for the second question, this is momentum, right?
Yeah.
You multiply, you divide the momentum by the amount of time the airplane
to get them.
Yeah.
goes over a length of one, right? Which is 1 over v. Right? So you basically divide this by 1 over v, which means you are multiplying this by v. So that's how much lift you get. All right. Okay, good. Thanks. All right, very good. I think the first answer, basically, it's integrating over constants, right? So the first answer you should get rho. It's minus. The momentum is negative. Rho times b times gamma. Okay. On the second one, you divide it by how much time the airplane travels over unit distance, which is 1 over v, right? So you divide by 1 over v, which means you multiply by 1 over v. So the airplane impacts a downward momentum with magnitude rho b gamma v on the air, which means the lift you get is rho b gamma v. Okay? So that's my lift. And if you express the strength of the vortex in terms of lift, you have this. Right? Okay. So this is why when we look at the helicopter, it's particularly scary. Like if you fly airplanes or drones, don't fly near a helicopter's wake, because it has a fair amount of lift, right? And you have a small velocity. I mean, helicopter flies slow, and it doesn't really have a big span, right? So high lift, low velocity, small span gives you a very strong vortex on the two sides of its the rotor disc. So you can get into very serious trouble flying helicopter's wake. Another thing that you don't want to fly around is something like this. Wind calm. Why did this happen? Right, very similar to what we saw before. So look at what the pilot is doing. Like for those who fly either airplanes, model airplanes, or real airplanes, you should know this is the aileron, right, of the airplane. And when the right aileron goes up, the left aileron goes down. Okay, so and when the right aileron goes up, it is trying to move the right wingtip downwards. And the left aileron goes down, it is trying to move the left wingtip upwards. It is trying to save the airplane, but there are just too strong of a vortex somewhere that prevents the airplane from being saved. Okay, so this is the airplane. So notice, like, this is another airplane that, for the same amount of lift, right, has a small flight velocity and the low wingspan. It's a biplane. All right. A biplane essentially gets twice the amount of lift within the same span of the wing, right? And a biplane doesn't usually fly very fast. Okay, so this is another case where this equation actually would tell you, if you know it, that like don't fly in its wake. All right. Okay. Now let's. What time is it? Okay. Maybe let me just pause over here and tell you a little bit more about explaining the lift. Not just explaining the lift, but also drag and other things. So here, we did an integral over really 3 spatial dimensions, right, of just the downward momentum. But imagine what else you can do. You have the whole velocity field expressed in formulas. You can integrate not just the downward momentum, but also the sideways momentum, right? That tells you how much force you get in the side direction. If you know the vertical structure, like this, right? I mean, in our case, you actually get 0 sideward momentum because the whole thing is symmetric. You can also integrate the square of the velocity to get what? Like half rho v squared to get what? If instead of integrating the rho times y velocity, if you integrate half of rho x velocity squared plus y velocity squared, what do you get? What?
Force.
Now, what is half rho v squared? It's actually, what is half mass times v squared? Kinetic energy. So half rho v squared is the kinetic energy per what? Volume, right. Okay, rho is mass divided by volume, right? So half rho v squared is half mv squared divided by volume. Okay, half rho v squared is the amount of kinetic energy per unit volume. And if you integrate that over a 3-dimensional space, what do you get? You get how much total kinetic energy is there in the wake, right? Okay. It is very similar to like our air cylinder model, except you can't just do half mv squared, or you have to integrate half rho v squared to get the total kinetic energy. And then you get induced drag. And you can derive how the induced drag depends on the vorticity distribution, right? And we'll start this in the next lecture looking at, okay, what if the vortices are not just the 2 sitting on the wingtips, but multiple, right? And how can we do momentum conservation to get lift? We can also see, we're not going to do any math to get the energy or rolling moments, but like we're actually going to like just to write down the formula, right? So if you have an airplane that tilts and have one side of the aileron up, the other side down, right? How is the rolling moment also going to display itself in the vertical wake? All right. Okay. See you on Friday.